For this tutorial, we're going to solve a problem related to packed tower. In this question, it is desired to remove 97% of acetone from gas stream containing 10 mole % of acetone in air by scrubbing with pure water in a packed tower filled with 50.80 millimeter metal pour rings. The given packing factor is 27 per feet or 89 per meter. The gas and water enter the tower at 10 meter cube per second and 5 kilogram per second respectively. The water possesses specific gravity of 1 and viscosity of 2.5 times 10 to the power of -3 kilogram per meter second. The process is to be operated isothermally at 300 Kelvin and total pressure of 101.3 kilopascal. In this question, we are supposed to solve the mass flow rates of the feed gas and the flow rates of extract, the pressure drops in the packing, the mass velocity of the gas at flooding point, and the diameter of the tower. This is a schematic diagram for the given question. In the questions, we are given the operating condition of the packed tower at pressure 1 atm and the temperature is at 300 Kelvin. So in this case, we're going to assume our component A to be acetone, component B to be air, and component C to be water. From the schematic diagram, water as a solvent is fed from the top of the column, and the mass flow rates of water given here is 5 kilogram per second, and it is a pure water. Therefore, the mole fraction for component C is equal to 1. At the bottom of the packed column, feed gas volumetric flow rate is given by 10 meter cube per second, and it consists of 10 mole % of acetone. Therefore, the mole fraction of acetone at the feed gas is 0.1. The rest of the component would be air. So in the feed gas, we have a mixture of acetone and air. Since it is required to remove only 97% of acetone from the feed gas, therefore 97% of acetone must be recovered at the extract. The rest, 3%, will be released at the raffinate. Please be careful with the unit used here. We can see that the flow rate of the feed gas is given in 10 meter cube per second, whereas the flow rates of solvent is given in kilogram per second. So, in order to determine the mass flow rate of the feed gas and the extract, so we need to do 2 steps, which is A, we need to determine the molecular weight of the feed gas. Next, we need to determine the molar volume of the feed gas. Based on the schematic diagram given here and all the data given here, we can proceed with to find the molecular weight of the feed gas. So we need to find the molecular weight of acetone, which is given by 58 kilogram per kilogram mole. Molecular weight of air is given as 29 kilogram per kilogram mole. Therefore, to find the average molecular weight of the feed gas, we just substitute the value of the molecular weight of acetone and air with the percentage mole that given in the question, and we can find that the molecular weight of the feed gas is 31.9 kilogram per kilogram mole. The next step that we have to do before we can determine the mass flow rate of the feed gas and the extract, we need to determine the molar volume of the feed gas at the given operating condition, 300 Kelvin and 1 atmospheric pressure. Therefore, we need to use combined gas law, which is P1 V1 over T1 equal to P2 V2 over T2. To use combined gas law that we have here, we need to determine first the first condition. The first condition is at standard temperature pressure, and the second condition is the operating parameter. Substitution of these values will be done for this particular formula to calculate for V2. So this V2 is actually the molar volume of the feed gas. So in this case, after doing the substitution, the molar volume of the feed gas is equal to 24.62 decimeter cube per gram mole, or equivalent to 24.62 meter cube per kilogram mole. So student, can you calculate the mass flow rate of the gas based on the data that we have in the previous calculation? Okay, now we can answer the questions. The first part of the question, so we can determine the mass flow rate of the feed gas and the mass flow rate of the extract. So the mass flow rate of the feed gas is given by 12.96 kilogram per second, and the mass flow rate of the extract is 7.28 kilogram per second. The second part of the question is to find the flooding pressure drops, and the formula given to find the pressure drops is 0.115 multiplied by the packing factor to the power of 0.7. So we're going to substitute the packing factor that we use, which is 27 per feet, and we get the answer for the pressure drops in inch water per feet is equal to 1.155. So to do the conversion into Pascal per meter, we need to multiply with the conversion factor, which is 817. Therefore, we can get the flooding pressure drops equal to 943.64 Pascal per meter or Newton per meter squared per meter. So this is our answer for the flooding pressure drops in the column. To determine the mass velocity of the gas in the column, there are a few steps that we need to do before we can get the final answer. So in this case, we have to determine the density of the gas and the density of the liquid. The density of the liquid is given by delta L, rho L, equal to 1000 kilogram per meter cube, and the density of the feed gas is rho G, and it is given by the mass flow rate of the feed gas over volume flow rate of the feed gas. Can you do the substitution to get the answer for the density of the gas? From the substitution, we get the density of the gas equal to 1.296 kilogram per meter cube. Do you get the answer? So based on the substitution that we have from the data that we have here, we substitute all data that we have calculated into the given formula to calculate abscissa value. Okay, we are going to use this graph to solve for the mass gas velocity. So we need to solve for the beginning. We have solved the abscissa value. From the abscissa value, we're going to sketch our flooding pressure drops curve, and then at the same time we're going to look at the value of the ordinate that we get. So this is the value of the ordinate, and then equate this equation with the ordinates that we have, and then solve for G prime, where our G prime here represent our mass gas velocity. From the previous calculation, we have delta P flooding is equal to 943.64 Newton per meter square per meter. And then for the abscissa, value, or x value, is equal to approximately 0. From the delta P flooding, the value that we have is 943. So it is approximately lies in between the approximate flooding of 800 to 1200. So therefore now we need to sketch the graph or the curve to get the approximate value. So now let's estimate the curve for delta P flooding that we have, which is 943. So we have 1000, we have 1200 at this point, and then 800 at this point. So if we were to have 1000, it should be in the middle, so it might be less than the middle part. So let's say the curve that we have is something like this. Okay, so we're going to estimate. So this is the value of our intersection between abscissa and the delta P flooding, and then we're going to draw the horizontal line here. Okay, so if we have to have here as 0.1, therefore here should be 0.15, and here is 0.2. Therefore approximately what we have here is 0.17 for our ordinate. So the data that we have previously, the packing factor is actually equal to 89 per meter. Density of the gas is equal to 1.255. Density of the liquid is equal to 1000. Gc, or the gravity constant, is equal to 1. J is equal to 1. Okay, and then the viscosity is given by 2.5 times 10 to the power of -3. And our ordinate that we get here is 0.17. Okay, so from these values we can calculate the value of gas mass velocity in the formula before we can calculate the diameter of the packed column. From the mass gas velocity that we have calculated, we're going to substitute the value here so that we can calculate the diameter of the tower. So we're going to find the cross-sectional area of the column, which is given by the mass flow rates of the feed gas over the mass gas velocity. So we're going to substitute the value 12.96 kilogram per second for our mass flow rate of the feed gas and divide with the mass gas velocity 2.117 kilogram per meter squared per second, and we get the area equal to 6.12 meters squared. So from the area that we have, we're going to calculate the diameter of the column or diameter of the packed tower. So based on the calculation, we get 2.79 meter as our diameter for the packed column.